Perhaps the single biggest global challenge is provision of pure water to the planet. Um, at this point in time, around 1/3 of the world's population does not have access to pure water. And as climate change is evolving, there are developed parts of the world which are running out of water, with some very well-known crises in California, Australia, and South Africa.
Thank you very much for joining me and in turn many other people who are going to be watching this to learn a little bit more about materials and about your career in science. So in that video, you told us that access to water is one of the big challenges facing us globally today. Would you be able to talk us through exactly how your work is helping to solve this?
Well, the problem, as it turns out, Emma, is not whether you can capture water, it's the cost. It's the energetic cost. So there are many materials, some of them naturally occurring, some of them synthetic, that can simply trap water from the air, like a sponge, essentially. The problem is recycling the material, is how much energy you need to put in to dry the sponge out. And for example, there's a class of materials known as zeolites. Zeo is boiling and light is lithos for stone. So they were named boiling stones. If you heat them up, you can see steam coming out of them. The problem is you have to heat them up to well over the boiling point of water. So a lot of energy is needed to capture the steam, if you like, that comes out of the stones, the boiling stones. So zeolites are very well known. They've been around a long time. You can dig them out of the ground. You can use them in kitty litter also, because they suck in the ammonia that's produced in kitty litter. But they're too energy intensive to be deployed for water harvesting. So that's the real problem, is it's all about the energy. Can you make it commercially viable with low energy?
This question is, obviously what you're designing can take water from the atmosphere, and it is such a great concept, but is there any negative impact in doing that, let's say, on the environment? If you were to put this in the Sahara, where there's not a lot of water in the atmosphere anyway, could it impact ecosystems or no?
Well, that's the beauty. The planet is one gigantic chemical reaction that's in equilibrium, right? So one of the first laws of thermodynamics is that if you perturb something, it will respond to fight that perturbation. So if you take water out of the air, then more water will go into the air from the oceans or the lakes or the rivers, right? So it's actually a perfectly harmonious situation. If you remove water from one part of the equation, the rest of the planet will respond to produce it and increase the humidity in the atmosphere. And we all know what dry means and what humid means from a human perspective. But from a quantitative perspective, 30% humidity is about the lowest anywhere on the planet. So the middle of the Sahara Desert can actually have quite a lot of water present in the atmosphere, but there's none in the ground. So if you were to pick the Sahara, there wouldn't be that much difference between capturing water vapor in the middle of the Sahara versus the Ireland, to use the other extreme.
Ireland is pretty humid. You talk a lot about finding global solutions for global problems. And obviously at the BT Young Scientists and Technology exhibition, we have students combating a wide range of problems. So how do you even begin to solve problems so large? Like, how do you design global solutions?
Well, it can't be done by one individual or one research group, or maybe even one country. It really requires a synergy between government, industry, and university researchers, because university researchers do the crazy stuff, right? They do the high risk things that might not work out, but some of them in the future will make a difference. And in terms of global challenges, some of them, it's obvious what they are. Access to pure water is one of them. Making solar energy much more efficient and commercially viable is another. Carbon capture is yet another. And by the way, carbon capture is not just for environmental reasons. CO2 is everywhere. CO2 is part of the atmosphere. It's also produced in many industrial processes, and you need to remove it. So there are a lot of technologies for carbon capture, just as there are for water capture. But it all boils down to the cost and the energy efficiency. And most people are aware that, at least from an engineering perspective, it's possible to remove the CO2 produced by hydrocarbon power plants. The problem is that the energy needed would mean you'd need to build 30% more power plants and consume 30% more energy. So it kind of defeats the purpose. You can do it, but the energy cost is so high. So for all of these examples that I just mentioned, the answer is simple: a new material that does a much better job than the materials we have today. And when we say better job, we don't mean, oh, it's 1% more efficient. We really need to reduce the energy footprints by 90%. So we need a revolution in material science. And I'm an optimist because I think this is easier than going to the moon, right?
Yeah.
But sometimes making people work together is harder than it sounds. So I think the obstacle is will and motivation and going about it the right way. It's not whether we can solve this problem, it's whether we have the will and motivation to do it before it's too late.
How did you actually become interested in material science in the first place? What inspired you to be in this field of study?
Oh, that goes back an awfully long way, but I remember it.
Oh, wow.
When I was a student, I was always naturally attracted to chemistry. Oddly enough, my best subject was geography. I always came number one in geography. I was always interested in the rest of the world and how the climate worked and how demographics worked. So I was always the number one student in geography. But chemistry is far more diverse and far more complex. And I was great in some parts of chemistry and terrible in others. But chemistry is what I got attracted to. Now, the end result is that I've traveled all over the world thanks to chemistry. So maybe there's a synergy there too.
So we might move on to the C- project. The goal is carbon negative farming, right? Would you be able to explain how that actually works?
Well, I mentioned how materials are the key to solving global challenges. Well, in this case, there are two global challenges at once. One of them is carbon capture, and the other is water harvesting. So obviously you can't grow plants without water, but you also can't grow plants without CO2. So CO2 is everywhere and is important and is good much of the time. So photosynthesis works. The first step of photosynthesis is carbon capture. And so C- is trying to combine the latest advances in carbon capture with the latest advances in water harvesting. And if you can capture water anywhere on the planet, and if you can capture CO2 to increase the CO2 levels to make the plants grow faster, then you can create decentralized farming. It would be a little bit like the hydroponics.
Okay.
A lot like the hydroponics, but you'd be able to set them up in the middle of the desert with no power source, because they would be self-sustaining from solar energy, powering the carbon capture and the water capture. But the objective is to create something which requires no energy, but takes carbon out of the atmosphere and produces a product that we all need, which is an edible plant.
And how close are we to a self-contained greenhouse? When do you think we would start to actually see this technology in use?
We started in September 2018. Within 1 year, we had a prototype material. And in less than 2 years, the first working machine was created. So it's a prototype, but there's actually a machine already that tests our materials for their ability to capture water from air. I wouldn't have thought that was possible, but it's possible if you have the right team. And I couldn't have designed that machine. They couldn't have designed the material. And you also need the will. And the person behind Molecule is personally motivated to solve the water purification problem for philanthropic reasons. There are commercial opportunities too, but was driven by a philanthropic approach. And the beauty is once you have the machine, if you have a better material, you just replace it in the same machine. And the machine is similar to what's used for dehumidification. So I would have said this was more than a long shot, but if you watch horse races, every now and then 100 to 1 horse wins, right? And that's really what this is about. If you have 100 to 1 shots, one of them is going to change things. So C- aims to take our best materials for carbon capture, our best materials for water harvesting, and combine them into a process for producing CO2 and water for farming, what we call decentralized farming. So you could set up a farm anywhere on the earth, right? With no electricity. That's the I think the dream.
Wow.
But we don't think it'll be that far away from its prototype. We think next year, by the end of next year, there could be a prototype demonstrating the technology, and then the technology will improve until it becomes more cost effective than the current approaches.
Yeah, it really is an incredible idea. It's incredible to think that this might be possible within our lifetime, really, would make a huge difference, wouldn't it?
Right, but to go back to the need for collaboration and teams, I'm not a biologist. I'm not a plant biologist. So one of the leading groups in Ireland at NUIG is part of this project too. And I'm not an economist who can evaluate carbon footprints and the costs associated. So all of these people need to come together. And it wouldn't have happened without the government challenging us to go there, right? So by providing seed money. So it needs a lot of things to come together. And Ireland, I think, is very good at this, at technology development, at government and industry working together with the universities. So that there actually is a reason to think that Ireland can be a world leader, not just in this area, but in other areas that require large projects that bring together a lot of team members from disparate areas.
My final question is, do you have any advice for the students that might have projects at the BT Young Scientists and Technology exhibition?
The same advice I give to all of my students is accept failure as a good thing, because failure teaches you ultimately how to succeed. So I'm not saying enjoy losing, don't be a loser, but accept that a failed experiment, if should inspire you to try harder to succeed. Because that's really what drives science, is we hear of the successes, but for every success, there were many failures. And you can apply the same thing to life. You're not going to get every job that you wanted. You're not going to get every grade that you wanted. But learning to live with failure and to embrace it and turn it into an advantage is my number one advice to all of the people that I work with, the younger people especially. Don't lose sleep if things didn't work out.
Well, thank you very much for joining us at the BT Young Scientists and Technology exhibition. I'm sure there are many people who have come away feeling very inspired by this, and especially about, I guess, your way of looking at how to solve big problems. So thank you very much for joining us.
Thank you so much, Emma.